This is part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to discuss the multipole expansion of the electrostatic potential. Previously, we discussed how to calculate the electrostatic potential due to a localized charge distribution. And that was equal to 1 over 4 pi epsilon naught, the volume integral of the volume charge density over the magnitude of the separation vector. We also investigated a number of examples involving boundary value problems, in which case where the potential was specified on a boundary and then the solution was made either inside or outside. Anyway, we looked at systems in Cartesian coordinates, cylindrical coordinates, and also spherical coordinates. However, those spherical problems were limited to situations where the systems exhibited azimuthal symmetry, which means that there's no phi dependence. So therefore, the potential could be expanded, summation L equals 0 to infinity over A sub L, R to the L, plus B sub L, R to the minus L plus 1, times the Legendre polynomial, P sub L cosine theta. And the coefficients A sub L and B sub L are determined by applying the boundary conditions. In today's lecture, I'm going to look at systems from a distance away. So we're going to calculate the approximate solution to a localized charge distribution, and that's going to involve making expansion of the separation vector. I'm going to do this several different ways so as to give you a different perspective on this problem, just looking at it slightly differently. And the reason why we're doing the multipole expansion, number one, if you have a very complicated charge distribution, this integral gets really ugly. So I'm going to make some approximations so the math is a little bit easier to handle. But that's not the only reason why we're looking at it. Next time around, or I should say an upcoming lecture, we're going to start looking at dielectrics. And dielectrics are essentially insulators. Now, when you place an insulator in an electric field, you might think at first, well, it's a neutral, it's composed of neutral atoms, so therefore, nothing's going to happen. However, that electric field is going to act on the charges that of which the atom is composed. Atoms are composed of positive charges and negative charges. That's going to lead to a little bit of a shifting in the charge, a little bit of a separation, and then the atoms are said to be polarized. Well, those polarized atoms, as it turns out, can be modeled quite well using the concept of the dipole. And we will be talking about dipoles in the context of the multipole expansion. So as I said, we're going to look at this a few different ways, but since I just mentioned dipoles, let's begin there. Composed of equal and opposite charges. I'll place charge minus q here at a distance or vector r prime with respect to the origin, and then I'll place another charge q that is going to be displacement d away from charge minus q, and therefore charge q is r prime plus d away from the origin. Now I'm interested in coming up with an approximate expression for this system, and such that we're very, very far away. So in other words, the separation vector r minus r prime is going to be much, much larger than the displacement between the two charges. And this is r minus r prime. Okay, so we've got the electrostatic potential due to these two charges. In the first case, we have charge q, and it'll be q over 4 pi epsilon naught, r minus r prime plus d. And then we've got the second charge, minus q, That's over 4 pi epsilon naught magnitude of the separation vector r minus r prime. I'm going to expand this quantity, this magnitude here in the first expression, or the first term rather. But I'm going to group them a little bit differently because the system, in this particular system, r minus r prime is a lot bigger than d. So I'm going to group those two terms together, and that'll be 1 over r minus r prime minus d. And I can rewrite that as r minus r prime squared minus 2 r minus r prime dot d plus d squared to the minus 1/2 power. I'm going to go ahead and factor out r minus r prime squared from each of these terms and pull it outside of the radical, so that'll be 1 over magnitude of the separation vector. And that'll leave 1 for the first term, minus 2 r minus r prime dotted into d all over magnitude of the separation vector squared plus d squared all over magnitude of the separation vector squared. Now I can make it a power series expansion because this expression is basically in the form 1 plus x to the minus 1/2, where x is a lot smaller than 1. Or actually just has to be smaller 1, but we're assuming it is quite a bit smaller. So this is 1 minus x over 2 plus 3/8 x squared minus 15/48 x cubed, and so on. Again, because of the assumption we're making that the separation vector r minus r prime is much, much larger than what separates the two charges. So I'm just going to keep the first two terms here, and that'll be 1 over r minus r prime times 1 minus 1/2 minus 2 times the dot product of the separation vector r minus r prime and d all over r minus r prime squared. Okay, so I'm going to go ahead and plug this expansion, or approximation rather, back up into my original exact formula. I'll pull out a factor of q over 4 pi epsilon naught, and I can also pull out a factor of 1 over r minus r prime as well, because each of these terms has that factor in common. So in the first case, this is going to be 1 minus, 1 plus r minus r prime dot d over r minus r prime squared. And then I have minus 1 as well. So the first two terms there, or rather the first term in this approximation and the contribution from the charge minus q, both of those cancel out, and we'll be left with q d dot r minus r prime all over 4 pi epsilon naught r minus r prime cubed. And there's a special name for this product of the charge and the distance that separates the two charges. That's just equal to the dipole moment, and specifically the electric dipole moment. I want you to keep that expression for the electrostatic potential due to a dipole in mind for what's coming up next, basically the approximate expression for the dipole, I'm going to make an expansion of 1 over the magnitude of the separation vector. And I'll write this as 1 over the square root r squared minus 2 times the dot product of r and r prime plus r prime squared. Our goal is to find an expansion for when r is greater than r prime. So in other words, the observation point is outside of the charge distribution. In fact, we really are interested for solutions that are is well outside the charge distribution. So r is definitely bigger than r prime. I'm going to pull out or divide each term through by a factor of r squared. Pull that out, r squared with minus 1/2. It's just going to be 1 over r. Now, because these two terms are less than 1, I can use that expansion that I wrote on the upper right side of the board. And these two terms play the part of x. Therefore, this becomes 1 over r out front of the square brackets, 1 minus 1/2 times parentheses minus 2 dot product of r and r prime over r squared plus r prime squared over r squared. And then the third term in the expansion has a factor of 3/8 out front. Times the same quantity in parentheses, only squared, and so forth. I next want to collect terms of equal order. So I want to write this out in terms of something times 1 over r, something times 1 over r squared, something times 1 over r cubed, and that's just going to leave it there. But the series goes on. So the first term is just going to be 1 over r. The terms that go as 1 over r squared, well, that would be the first term inside the first parentheses. That'll be the dot product of r and r prime, all over r cubed, and yes, it does go as 1 over r squared because you do have a factor, you do have an r up in the numerator. Okay, so now we're looking for the terms that go over as 1 over r cubed. That'll be the second term from the first set of parentheses. And that's r prime minus r prime squared over 2r cubed. And there'll be one contribution from the second set of parentheses. You got a 3/8 out front. And so forth. So that's 3/8 over r minus 2r dot r prime over r squared, all squared. Let me just rewrite this a little bit. And that's actually just the same thing as 3/2 the dot product of r and r prime squared all over r to the 5th. I'm going to insert this expansion back into the expression for the electrostatic potential. We have 1 over 4 pi epsilon naught out front, volume integral, volume charge density, 1 over r plus r dot r prime over r cubed plus uh, 3/2 dot product of r and r prime squared, 1 over r plus r dot r prime over r cubed plus 3/2 dot product of r and r prime squared all over r to the 5th. And that's 1 over 4 pi epsilon naught out front, volume integral, volume charge density, 1 over r plus r dot r prime over r cubed plus 3/2 dot product of r and r prime squared minus r prime squared, r squared over 2. And then we get a factor of 1 over r to the 5th out front. But again, that does in fact go as 1 over r cubed, and so forth. Let's break this down term by term. The first term in the expansion is the monopole term. And that is equal to 1 over 4 pi epsilon naught r. You can pull the r out front because we're just integrating over the prime quantities. And essentially it's just the volume integral over the volume charge density. Well, that's just the total charge in the system. So basically what this term is telling you is if all the charge were concentrated at the origin. The next term is the dipole term. I'm going to pull out 1 over r cubed. But I can also pull out the r dot as well because, again, it's not a prime coordinate. And this quantity here is just the dipole moment. So if you think back to the previous derivation that we went through, notice the similarity in forms. But here we are expanding about the origin of the coordinate system. Okay, the third term is a quadrupole term. And maybe I'll write this out. Pull a factor of 1/2 out as well, in addition to the r over 5. And in fact, there's a convenient way of writing this in terms of tensors. Or a tensor, I should say. And basically this is equivalent to a double summation over xi, xj over r to the 5th. X and I and xj represent Cartesian coordinates, x, y, and z. And furthermore, left out something critically important there. That last term that I just scribbled in there is called a Kronecker delta. And that has value of 1 if I and j are equal to each other, and 0 otherwise if I and j are not equal to each other. I can write this in a little bit more convenient fashion if I'd only left myself enough room here. Let me write it over here. replace that integral by the tensor Qij. And as we'll see that this tensor is in fact symmetric, and well, when we get into azimuthal symmetry, what we'll notice is that the off-diagonal terms of this will drop out, and it also will be a traceless tensor as well. So anyway, that is the expansion. Let me just write it all together. First term is the monopole term, it's just Q total, total amount of charge in the system over 4 pi epsilon naught r. Second term is the dipole term. And that's the dot product of r and the dipole moment over 4 pi epsilon naught r cubed. And then finally we've got the quadrupole contribution. And I don't want to have that up there. And there are the first 3 terms in the expansion: monopole, dipole, and quadrupole. Okay, so let's consider, answer the question, what terms do drop out if the system presents azimuthal symmetry? So in other words, the charge density only depends on r and theta, doesn't depend on phi. Let's consider the monopole term first. Basically, it's useful to express this in spherical coordinates. Just easier to do the calculations that way. Okay, so Q total is just equal to the volume integral over the volume charge density, which just depends on r prime theta prime. So when we do the integral over the phi coordinates, that's just going to get a factor of 2 pi. So if you have azimuthal symmetry, the monopole term remains. And it will be non-zero, of course, only if there is net charge in the system. If the total charge in the system vanishes, then the monopole term will vanish as well. But generally speaking, it will certainly, monopole per term will certainly be there even when there is azimuthal symmetry. Okay, so that's one down. Now what about the dipole terms? So just let's rewrite this out. The dipole is equal to the volume integral over r prime and the volume charge density. We need to consider each of these terms separately. So let's look at the x prime, or the x component first. Oops, I don't want to pull that out, do I? Okay, so this piece of x, and that's equal to x caret x prime, okay? And again, you want to rewrite x in terms of spherical coordinates. So let me pull this over to the left a little bit more. So that's going to be r prime sine theta prime cosine phi prime. And you're going to multiply that by the volume charge density, which does not depend on phi. And we'll do the math. Well, you see the problem here when you integrate the phi term. the cosine phi prime from 0 to 2 pi, that's just equal to 0. So p sub x drops out. If there's azimuthal symmetry. Now, what about py? Well, azimuthal symmetry means that you've got symmetry about the z-axis, so you don't really even need to go through this step, but I will anyway. Let's look at the y component. So basically, I'm calculating the volume integral over y prime, which is r prime sine theta prime sine phi prime, times the volume charge density, and in this case, be integrating over sine phi prime going from 0 to 2 pi, which again is 0. So px drops out, py drops out, p sub z will not, as we'll see presently. So instead of having r prime sine theta prime sine phi prime, basically be doing the integral of r prime cosine theta prime. Remember, that's just equal to z prime, okay? So there are no other factors of sine phi or phi prime or cosine phi prime within this integral. Therefore, integrating over from 0 to 2 pi over phi, it's just going to give you a factor of 2 pi. So in azimuthal symmetry, pz remains. Now let's look at the quadrupole tensor and see which terms contribute in that case. And unfortunately, I am going to have to give myself some more room, so I need to erase this. This tensor has 9 elements. So I want to look at this interval and see which terms survive azimuthal symmetry. And it's just, we're looking at this volume interval of 3x I prime xj prime minus product or delta r prime squared, all times volume charge density, integrating over the volume. Let me just write this in terms of r prime theta prime, and of course the volume element r prime squared dr prime sine theta prime d theta prime d phi prime. Let's look at the off diagonal terms first. As I already said, and I'm going to show right now, these will all vanish. I want to take a look at I equals 1, j equals 1 first. That corresponds to, let's do j equals 2. So that corresponds to x and y. So when I and j are not equal to each other, this second term drops out, and we are looking at an integral of the form 3x prime xj prime rho r prime theta prime. And let me write this way over here, r prime squared dr prime sine theta prime d theta prime and d phi prime. And let me move this over here as well to give myself a little bit more room, okay? So in this case, we are looking at the integral of 3x prime y prime. Again, it's most convenient to rewrite these in terms of spherical coordinates, so that becomes r prime sine theta prime cosine phi prime, and r prime sine theta prime sine phi prime. So I get the product of two trigonometric functions, cosine and sine, And if you do the integral of those two from 0 to 2 pi, well, one way of writing the integral is just sine squared phi prime all over 2 to 0 to 2 pi. That's just equal to 0. So qxy is equal to 0. But as you can see, this is a symmetric tensor. So therefore, qxy is equal to 0, so is qyx. Okay? Let's look next at x and z. Do the integral 3x prime z 3x prime z prime. Let me replace those by their, or write them in terms of their spherical coordinates. It's r prime sine theta prime cosine phi prime and r prime cosine theta prime. Okay, so when I do the math here, what will I wind up with? I'll wind up with an integral over cosine phi prime, just going from 0 to 2 pi. That is equal to 0. So therefore, qxz is equal to 0, and qyz, I'm sorry, qzx is equal to 0 as well. And last but not least, let's look at what happens if we look at the coordinates y and z. Okay, so it'd be 3y prime z prime, and then wrote everything else out in spherical coordinates. So let me replace these by their spherical coordinates. So this is r prime sine theta prime sine phi prime, r prime cosine theta prime. And again, you don't need to write it out. You're doing the integral from 0 to 2 pi over sine phi prime. So that's also equal to 0. So for a quadrupole, or the quadrupole tensor, all the off-diagonal terms drop out. And I won't write it out, but in fact, all the diagonal terms do remain. Those are non-vanishing. But there is a relation between the diagonal terms of the tensor, and that makes life a little easier if you have a relation, so you don't have to calculate as much. Okay, so let's look at that next. And again, unfortunately, I'm going to have to erase this bottom part. So essentially, we've got integrands that contain 3x prime squared minus r prime squared. So this is corresponds to the qxx element. I'm going to leave a little bit of all of this off because it is getting a little bit messy here. But anyway, this is what this term is going to be equal to. And then you have 3y prime squared minus r prime squared. And got 3z prime squared minus r prime squared. Okay, so when you do the integral, basically whether you integrate over the x prime squared or y prime squared, those two answers are going to be the same. So one of the results here is that qxx is equal to qyy, or if you want to stick with the dummy indices, that's q11 is equal to q22. Now what about comparing this with this? How are qx and qy related to qzz? Okay, so if it's symmetric, and again, I'm not saying that these are equal to each other, but just imagine that this is inside of an integral. So when I do the integral over this, it's the same thing if I just said, well, this is just 2x prime squared. Not saying that they're identical to each other, okay? Just the integral over them. Now, how about down here? This is 3z prime squared minus r prime squared, so we can write this rx prime squared, y prime squared, plus z prime squared. And once again, I can say, well, once I do the integral, it's really the same thing if I just had 2x prime squared. Okay? So when I write this out, this is going to be x prime squared minus z prime squared. And down here, this is 2z prime squared minus 2x prime squared. So you see the relation between these two. Basically, qzz is equal to minus twice a qxx, and it's also equal to minus twice a qyy. So it's really, really just have one element to calculate out of the potential line, one element or one component of the dipole moment to calculate. Okay, so let me just leave this up here for a minute before we wrap the discussion up of azimuthal symmetry in general before we get on to an example. So we just have Q total over 4 pi epsilon naught r. We got Z PZ over 4 pi epsilon naught r cubed. Okay, and I could go a step further and just replace these, write these all in terms of Q C Z Z. And that is times, that's not 24. Okay, so it's 1/2 over, and 1 over 4 pi epsilon naught r to the 5th, x squared qxx plus y squared qyy plus z squared qzz, and so forth. So let's say, well, what happens if we just evaluate this potential along the z-axis, okay? So I'm going a step further. Not only does the system present azimuthal symmetry, but I'm also going to calculate the potential just along the z-axis. And I'm going to go ahead and rewrite this in with the integrals present. So this is volume integral of volume charge density Okay, so all I'm doing is I'm just going to write this, this expansion just as if I'm evaluating it at r equals z. So these two terms, nothing drops out, but when I write the third term down, the term to do the quadrupole, because we are evaluating along the z-axis, this term and this term drop out because x and y are going to be 0 then. So therefore, you're just going to have this final term will be present, so I pull z squared over, and it'll be over 8 pi epsilon naught r to the fifth, and we have our volume integral. And then inside, we're just going to have the qzz term corresponds to, or the element rather, is the volume integral over volume charge density, 3z prime squared minus r prime squared. And again, I'm going to rewrite this in spherical coordinates. And I'll pull out the r prime squared. Okay. And actually, I should move this back under inside the integral. So what's going on here? Notice that there's a pattern. If you look at the integrands, we've got 1 times the volume charge density. We've got r prime cosine theta prime times the volume charge density. And down here, we've got r prime squared times volume charge density times 3 cosine squared theta prime minus 1 over 2. What are all those cosine theta prime terms amount to? Those are just Legendre polynomials. So this has a factor of P0 cosine theta, that's just equal to 1. This has a factor of P1 cosine theta prime, should use a prime here as well. This is just P2 cosine theta prime, and so forth. Okay, so therefore, the potential along the z-axis for a system that presents asymmetrical symmetry can be written in a nice, neat form. 1 over 4 pi epsilon naught, summation L equals 0 to infinity. In the denominator, I'll just leave this as r, but remember r is equal to z in this case, so that's just r to the L plus 1, and it's 1 over that. And then we have our volume integral, volume charge density. Inside the integral, we have r prime to the power L, and then you have PL cosine theta prime, and this is again integrated over the volume. Okay? And again, this result applies when r is equal to z. Okay? And for a system that presents asymmetrical symmetry,